Limit comparison test. Let's continue on in our journey of determining whether an infinite series converges or diverges by now looking at the limit comparison test, or LCT. Suppose a sub n and b sub n have non-negative terms for all n greater than or equal to some capital N, where capital N is some integer. So this really just means eventually. Eventually, these two sequences of numbers, a sub n and b sub n, have non-negative terms. All right, so let's take a look at what we have here. If the limit as n approaches infinity of a sub n over b sub n is equal to a finite number c that's greater than 0, then the sum of a sub n and the sum of b sub n both converge or they both diverge. Let's try to make sense of this graphically. Here I have two sequences, a sub n and b sub n, with non-negative terms graphed. Let's think about the limit as n approaches infinity of a sub n over b sub n, and what it means for that limit to be some positive constant. So since we're thinking about n approaching infinity, we're thinking about the tail end of each of these sequences. So we really don't focus on what's happening at the beginning, we're focusing on what's happening at the end. And what's happening at the end is that the ratio, a sub n over b sub n, the ratio between these outputs is a constant. So these are scalar multiples of one another. We can think about it as they're kind of hugging each other as they are both heading off towards 0. And what that means about their corresponding series is that their series are going to have the same behavior. They're either both going to converge or both diverge. So if we think about adding up all of the outputs here for the b sub n sequence, if that happens to be a finite number, and a sub n is basically, again, hugging or a scalar multiple of b sub n, well, then adding up all of the terms of a sub n is also going to be a finite number, and it's also going to converge. And similarly, if we add up all of these b sub n outputs, and those don't add to a finite number, so this series diverges, then the one that was basically following along next to it will also diverge. The limit comparison test has a few more pieces. If the limit as n approaches infinity of a sub n over b sub n happens to be 0 rather than a positive value, then we also need the sum of b sub n to converge for this to tell us anything. So if we get that the limit of this ratio is 0 and the sum of b sub n converges, then we can conclude that the sum of a sub n converges. Finally, if the limit as n approaches infinity of the ratio a sub n over b sub n equals infinity, then we also need that the sum of b sub n diverges to conclude anything. We can then conclude that the sum of a sub n diverges. So I will say when we attempt to use the limit comparison test, we are aiming for the first case to happen. But if we end up getting the limit of the ratio to be 0 or infinity, we have to take that extra second to think about whether the comparing series converges or the comparing series diverges to determine whether that's going to be helpful. Let's jump into an example. Does the sum of n equals 1 to infinity of 2 to the n over 5 to the n minus 3 converge or diverge? We do want to move forward with the limit comparison test here. And just like the direct comparison test, we're hoping to find a geometric or p-series to compare it to, because those are really easy to determine convergence or divergence of. So here what we're going to do is attempt to compare this to the geometric series 2 to the n over 5 to the n. So the sum of n equals 1 to infinity of 2 to the n over 5 to the n, that's the sum of 2/5 to the n. And we can see that the common ratio r is 2 over 5. So the absolute value of r is less than 1. So what that means is that we have a convergent geometric series. Now, to apply the limit comparison test, we're going to take the limit as n approaches infinity of our general term, so 2 to the n over 5 to the n minus 3, over the general term of the nice series, hopefully again geometric or p series that I'm comparing it to. So 2 to the n over 5 to the n. All right, let's go ahead and rewrite this as 2 to the n over 5 to the n minus 3 times the reciprocal 5 to the n over 2 to the n. Well, we can actually cancel out the 2 to the n's. We cannot cancel out the 5 to the n's because of the minus 3 here. But if we are thinking about the limit as n approaches infinity, the top is dominated by 5 to the n, the bottom by 5 to the n, because the minus 3 towards infinity doesn't really matter. So 5 to the n over 5 to the n is just 1, which is greater than 0, but we also have to be very careful and put and finite. So it's not enough to say greater than 0 because infinity is greater than 0. We need to be clear that the output here is a finite value. So once we've stated that, we can draw our final conclusion. We can write by the LCT, limit comparison test, since the sum of n equals 1 to infinity of that 2 over 5 to the n converges, we showed up here that it was geometric, then the sum of n equals 1 to infinity of 2 to the n over 5 to the n minus 3 also converges. So yes, we do have to write all of the formality here showing the comparing series, how it converges or diverges, the limit as n approaches infinity of the ratio, and state that that value is positive and finite, and then state that we were using the limit comparison test and what the final conclusion is. If on this one you were thinking about trying the direct comparison test, unfortunately that doesn't work. If we think about 2 to the n over 5 to the n compared to 2 to the n over 5 to the n minus 3, 5 to the n is a bigger denominator, so this left side is a smaller fraction overall. And we know 2 to the n over 5 to the n as a series converges, so I have a smaller converging series, and so that is not helpful. So we cannot apply the direct comparison test here. We would move forward with the limit comparison test. In this example, we want to know, does the sum of n equals 1 to infinity of the cube root of the quantity n to the 5th plus 1 over n squared plus 2 converge or diverge? So for this one, we are going to use the limit comparison test. And now it's a matter of deciding what are we going to compare it to? And when we have an algebraic function like this, what we want to do is look to what's basically the leading piece of the numerator and the leading piece in the denominator. So in the numerator here, I'm going to focus on the cube root of n to the 5th. So I'm going to have the sum of n equals 1 to infinity of the cube root of n to the 5th over, in the denominator, n squared. And so I'm going to think about this and how I can simplify it because it's really a p series. So I have the sum of n equals 1 to infinity of n to the 5/3 over n squared. And 5/3 is less than 2, so I can subtract 5/3 from 2 here. So I have the sum of n equals 1 to infinity of 1 over n, and then I really have 2 minus 5/3. Well, 2 is 6/3, so what I have going on here is the sum of n equals 1 to infinity of 1 over n to the 1/3. So this is a p series. P is equal to 1/3, which is less than 1, so this is a divergent p series. All right, so we have that down. Now let's go ahead and set up our limit as n approaches infinity of our given a sub n, so the cube root of n to the 5th plus 1 over n squared plus 2 over the series that we're going to compare it to, general term, 1 over n to the 1/3. Now, what we probably want to start to just get in the habit of is, instead of setting up a quotient over a quotient, jumping straight to the reciprocal of the denominator. So the limit as n approaches infinity of the cube root of n to the 5th plus 1 over n squared plus 2 times n to the 1/3 over 1. All right, so now we have to be able to justify this answer in our head. And what's happening here is this piece is, again, basically acting like n to the 5/3 towards infinity. And then I have this extra n to the 1/3. So the numerator up here is sort of acting like, so I'm going to put it in quotes, it's like n squared up here. So 5/3 and 1/3 is 6/3, which is 2, an exponent of 2. So the top up here is like n squared. And the bottom is dominated by n squared. And so since they're the same degree, their coefficients are just 1. So the answer here is just 1 to this limit at infinity, which is greater than 0 and finite. So we can draw our conclusion. We can say by the limit comparison test, since the sum of n equals 1 to infinity of 1 over n to the 1/3 diverges, our given series also diverges. Here, does the sum of n equals 1 to infinity of 3n squared plus 5n over 2 to the n times the quantity n squared plus 4 converge or diverge? So for this one, it's a matter of thinking about what are we going to compare this series to. So let's think again about the pieces that dominate the numerator and denominator. In the numerator, we have 3n squared. In the denominator, I have 2 to the n times the quantity n squared plus 4. So if I thought about distributing in the 2 to the n, the dominating piece would be 2 to the n times n squared. And so if I think about taking those pieces and simplifying them down, so the sum of n equals 1 to infinity of 3n squared over 2 to the n times n squared, well, the n squareds actually cancel out. And so I have just the sum of n equals 1 to infinity of 3 over 2 to the n, which is a convergent geometric series. So in fact, I don't even have to take the 3 with it. I can just focus on the sum of n equals 1 to infinity of 1 over 2 to the n, which is the sum of n equals 1 to infinity of 1/2 to the n. Now you could take the 3 with it if you want. I'm just going to take 1 over 2 to the n, which is a convergent geometric series. So r is 1/2. The absolute value of r is less than 1. So this is a convergent geometric series. And now let's go ahead and take the limit as n approaches infinity of our original general term here. So 3n squared plus 5n over 2 to the n times the quantity n squared plus 4. Now, instead of dividing by 1 over 2 to the n, I'm going to jump straight to multiplying by the reciprocal. So we're going to have times 2 to the n over 1. And so notice what's going to happen is that the 2 to the n's will actually cancel out. And now we're just evaluating the limit as n approaches infinity of a polynomial over a polynomial. And these polynomials have the same degree, n squared, n squared. And so I can just take their coefficients, which would just be 3 over 1. So the answer to this limit at infinity is 3, which is greater than 0 and finite. So the output of the limit at infinity doesn't have to be 1. The last two examples were 1. It could be any positive finite value. And then the two series will have the same behavior. So we compared it to 1 over 2 to the n, which was a convergent series. So we can draw our final conclusion. By the limit comparison test, since the sum of n equals 1 to infinity of 1 over 2 to the n converges, right? It was geometric. Then our given series also converges. They have the same behavior. Now here we have, does the sum of n equals 1 to infinity of tan inverse of n over n squared converge or diverge? So here, what are we going to compare this to? Well, I would go ahead and choose the p series 1 over n squared and see what happens. Because again, p series are nice. We can easily conclude the sum of 1 over n squared is a p series with p equal to 2, which is greater than 1. So this is convergent. So what we need to do from here is take the limit as n approaches infinity of tan inverse of n over n squared, our original general term, and then divided by 1 over n squared. But as we said, let's just jump straight to multiplying by the reciprocal, n squared over 1. And something nice is going to happen here. N squared is going to cancel out, and we're just taking the limit as n approaches infinity of tan inverse of n. And this is a graph that we should definitely be familiar with. We know that tan inverse towards positive infinity over here is approaching pi over 2. So this is pi over 2, which is greater than 0 and finite. So we can make our conclusion using the limit comparison test that our given series has the same behavior. It is also convergent. So here is that formal write-up again, where we state that we found this by the limit comparison test. Now, just real quick, on this one, we could have actually used the direct comparison test with 1 over n squared. So if we think about tan inverse of n, we know that tan inverse of n is less than pi over 2. So the same reasoning we have here is less than pi over 2. So let's divide both sides by n squared. And what we have is now on the right-hand side, essentially a p-series. So we have a pi over 2 times 1 over n squared. So if I think about 1 over n squared, that is converging, and it's bigger than tan inverse of n over n squared. So I have a converging bigger series. Whoops, converging and bigger. And so that is a helpful direct comparison. So that was an option on this one. And maybe one that was worth trying at the beginning. So how can you tell which test to use and when? I really wouldn't use the direct comparison test personally if it wasn't just like a nice function over a nice function, or it's just off by a number, versus, let me just rewrite the last example that we looked at real quick. The last example had so much going on. 3n squared plus 5n over 2 to the n times n squared plus 4. So on something like that, I would not go to the direct comparison test. It might be a little bit harder to justify the inequality versus if you just kind of have one term on the top and one term on the bottom, or you're just off by a number, then it might be worth it to try the direct comparison test. So it is just going to be a matter of practice to sort of recognize what is a good thing to try, and we might just have to try more than one test, and more than one test might work. For this example, does the sum of n equals 1 to infinity of the quantity natural log of n squared over radical n converge or diverge? I am going to attempt to move forward with a limit comparison test, and I want to go ahead and try to compare it to the sum of n equals 1 to infinity of 1 over the square root of n, because that is a p-series, and this p-series has p equal to 1/2, which is less than 1, so it is a divergent p-series. Now let's see what happens when I attempt to take the limit as n approaches infinity of the ratio of these two general terms. So I'm going to have natural log of n quantity squared over the square root of n times, let's jump straight to the reciprocal of 1 over radical n, we have radical n over 1. And so those are going to cancel out, and what we have is the limit as n approaches infinity of just natural log of n squared. And natural log n towards infinity is going to infinity, and then when you square it, still going to infinity. So our answer is infinity. It's not a positive constant, but that doesn't mean the limit comparison test has failed us yet. It depends on whether the series we're comparing it to converges or diverges. So the one that was helpful, if we get out infinity, is if the one we're comparing it to is divergent, and it is. So this is also able to be determined by the limit comparison test, but one of those latter cases. So it's actually the third case there. So we are able to put our conclusion by the limit comparison test since the sum of 1 over the square root of n diverges, right? And because this limit was infinity, we know that our series, the sum of natural log n quantity squared over the square root of n, that also diverges. So this was helpful, but only because the series we were comparing it to was divergent and we got out infinity when we did the limit of the ratio of the general terms. On this example, does the sum of n equals 1 to infinity of the quantity natural log of n squared over n cubed converge or diverge? All right, so if we try to move forward with the limit comparison test and we attempt to use the sum of 1 over n cubed, similar to the last example, let's see what happens. So we have p is equal to 3, which is greater than 1. So we have this is a convergent p series. And let's go ahead now and try to take the limit as n approaches infinity of our general term, natural log of n squared, over n cubed times the reciprocal of 1 over n cubed, so n cubed over 1. The n cubed cancel. As n approaches infinity, we get infinity. So this is not a positive constant, and the series we were comparing it to is convergent. So this was not helpful. We cannot use the limit comparison test, at least with 1 over n cubed. So that did not help us. So what does that mean? We can go ahead and try another limit comparison or a direct comparison. I'm going to try another limit comparison. So the obvious one to choose was sort of 1 over n cubed, but I'm going to go ahead and pick 1 over n squared. And let's go ahead and see what happens. So if I choose 1 over n squared, that's still a p series. P equals 2, which is greater than 1. So it's a convergent p series. But the main difference is what's going to happen when I take the limit as n approaches infinity of my natural log of n squared over n cubed times n squared over 1. So we are going to have some stuff cancel, n squared and 2 copies of n. So we have natural log of n squared over n. And so let's go ahead and think about what happens to that limit. So the limit as n approaches infinity of natural log n quantity squared over n. Well, here, I don't think it's totally obvious which one is growing bigger faster because natural log n is being squared, and then I have n on the bottom. So I'm going to use L'Hopital's rule just to be sure here because I have, an infinity over infinity case. So if I use L'Hopital's rule, I'm going to put a little LH for L'Hopital's rule. Then I'm doing the derivative on the top with a chain rule, 2 natural log n to the first times 1 over n over the derivative of n on the bottom, that's 1. Okay, so now what do I have? I'll rewrite it. The limit as n approaches infinity of 2 natural log n over n. Well, now I'm sure n is a polynomial that grows bigger faster than natural log n, so this goes to 0 this time. This is still one of those special cases because 0 is not a positive finite number. But if we get 0 and we compare to a convergent series, then our given series converges. So this is sort of that other special case, or really just not common case. So since we got 0 here, we can draw our conclusion using the limit comparison test. We can put by the LCT since the sum of 1 over n squared converges, our given series also converges. Now, if we decided to sort of quit right away when we found out that the 1 over n cubed comparison was not helpful and went for the direct comparison test, we could do that. That one, I think it ends up being just a little bit harder to really convince myself of the comparison, but it would work. So if I try a direct comparison, I just kind of want to show you what would work. So if we start with the idea that natural log n is less than the square root of n, and so we would know just this comparison just from the dominance of functions. So natural log n is less than the square root of n. Then let's square both sides. So over here I have natural log of n squared. So if I square both sides, natural log of n squared would still be less than squaring the square root of n, and that's just n. And now let's divide both sides by n cubed. So we'd have natural log of n squared over n cubed. That's less than n over n cubed, which is 1 over n squared. So this is helpful because 1 over n squared is a convergent p-series when you think about the sum. And so since that's bigger, right, greater than, and convergent than this general term, then we know our series converges by the direct comparison test. So we could have used a direct comparison. It all really kind of starts with the idea that natural log n is less than the square root of n, of course, for positive numbers, and then our ability to go from there and create a comparison to a known convergent series. Now let's talk about the common question of when should I use the limit comparison test, especially because there is a direct comparison test. Well, usually you try to use the limit comparison test when your series has multiple polynomial terms, roots, or messy algebra. So for example, the sum of n equals 1 to infinity of 4n plus 5 all over n squared plus 2n plus 3. So lots of polynomial terms. We would try to use the limit comparison test. The sum of n equals 1 to infinity of n plus 1 all over the square root of the quantity n to the 6 plus 4, or the sum of n equals 1 to infinity of the square root of the quantity n squared plus 4n plus 1 all over n cubed plus 1. So basically, again, multiple polynomial terms, roots, messy algebra. And the idea is that if you can find a simple series that behaves the same way for large n, try the limit comparison test. And so what we're going to do to find that simple series is we're often going to focus on those dominating terms in the numerator and in the denominator to think about what to compare it to. So in practice, it means keeping only the highest power term in the numerator and in the denominator. And even when something is a good candidate for the direct comparison test, the limit comparison test will often work too. And in general, I prefer the limit comparison test rather than the direct comparison test. So even though something might be a candidate for direct comparison, if you can kind of look at your general term and it behaves the same way for some large n, then try the limit comparison test on it. It's probably going to be a little bit quicker to do. And finally, for either comparison test, we can only use this if we have positive term series.